Imagine a lake that can kill nearly 1,800 people in minutes, not by drowning, but by suffocation from invisible gas. This hidden danger reveals the profound power of water's unseen physics, sculpting aquatic worlds and holding life and death in its layers. We'll explore why some lakes remain stubbornly separated for centuries, unlike most, and how these hidden structures can unleash catastrophe. You might think of a lake as one continuous body of water, but beneath the surface, an invisible architecture is at work. Most lakes, especially in temperate regions, are actually divided into distinct thermal layers. This phenomenon is called lake stratification. The top, warmest layer exposed to sunlight and wind is known as the epilimnion. Below it lies the metalimnion, or thermocline, a crucial middle zone where temperature changes rapidly. And at the very bottom, isolated from the surface, you find the colder, denser hypolimnion. What creates these distinct layers? The primary physical mechanism is a unique property of water itself. Water is most dense at 4 degrees Celsius, or 39 degrees Fahrenheit. Crucially, it becomes less dense at temperatures both warmer and colder than this point. This means that warmer water will float above colder water, and colder water will sink beneath warmer. It's a fundamental principle, an invisible architect, dictating where water will settle in the lake basin. In many temperate lakes, this thermal architecture is dynamic. They are dimictic, meaning they mix twice a year, typically in spring and autumn. This process, known as turnover, is vital. It replenishes oxygen in the deeper waters, allowing life to thrive throughout the lake. Without it, the hypolimnion would quickly become depleted of oxygen. This natural mixing prevents a fate that befalls a rare, dangerous few, a phenomenon we will explore in depth. But not all lakes conform to this annual rhythm. There exists a rare type of lake where the water layers do not intermix for extended periods, spanning years, decades, or even centuries. These are called meromictic lakes, a term coined by Austrian limnologist Ingo Findenegg in 1935. Unlike their holomictic counterparts that mix at least once annually, meromictic lakes harbor permanent, invisible walls. They represent an extreme example of water's stratification power. Meromictic lakes typically feature 3 stable layers. The top layer, the metalimnion, behaves much like a regular holomictic lake, experiencing some seasonal mixing. Below it, however, lies the chemocline, an intermediate layer defined by sharp chemical gradients. This isn't just a temperature shift, it's a barrier built from dissolved substances. And beneath the chemocline, the deepest layer, the monolimnion, circulates very little, if at all. The lack of mixing in these lakes is often due to chemical stratification. Differences in dissolved substances, particularly salts, significantly increase the water density in the lower layers. This makes it far harder for these dense, saline layers to mix with the less saline upper waters, creating a more robust, enduring barrier than temperature alone. This phenomenon is called ectogenic meromixis when external factors, such as saltwater intrusions into coastal lakes or even runoff from road salt, create this dense, saline bottom layer. It's a powerful testament to the architects at work. The consequences for the monolimnion are profound. Being cut off from oxygen replenishment, this bottom layer becomes severely oxygen-depleted, anoxic or hypoxic. This restricts most aquatic life that requires oxygen. Yet these extreme conditions don't mean a lifeless void. Instead, they can support unique microbial communities, such as vibrant purple sulfur bacteria, thriving where little else can survive. Conditions here are truly alien, sculpted by these invisible walls. The undisturbed nature of sediments in meromictic lakes also creates a unique scientific record. Due to minimal physical mixing and chemical decomposition in the anoxic monolimnion, these lakes preserve layered annual deposits called varves. These varves offer invaluable paleolimnological records, acting like tree rings for the lake, allowing scientists to look back through centuries of environmental history. But what happens when these invisible walls are not just boundaries for life, but traps for disaster? What are the ultimate stakes when these layers refuse to mix? In 1986, the world witnessed the catastrophic potential of meromictic lakes at Lake Nyos in Cameroon. A sudden release of dissolved gases, primarily carbon dioxide, from the deep, unmixed layers caused a limnic eruption. This unseen force, a massive CO2 cloud, suffocated nearly 1,800 people and thousands of livestock. This wasn't an isolated geological anomaly. The Black Sea, for instance, is considered the world's largest meromictic basin. Below approximately 50 meters, or 160 feet, its waters do not mix with the upper layers. The result? Over 90% of its deeper volume is anoxic. Think about the sheer volume of water rendered lifeless, a staggering scale of stratification. It's a permanent, immense monument to water's invisible architects. Even in seasonally stratified lakes, the consequences of these layers are significant. Thermal stratification results in the accumulation of nutrients, particularly phosphorus, in the hypolimnion during warm months. When oxygen in the hypolimnion runs out, these nutrients can be released from the sediments. This can fuel problems like algal blooms when the lake eventually mixes, impacting water quality. The timing and intensity of lake stratification globally are being altered. Human influences, including land use changes, increasing air temperatures, and shifts in weather patterns, are directly impacting these delicate structures. The invisible architects are reacting to our presence, with consequences we are only beginning to fully understand. Meromictic lakes, while rare, serve as vivid examples of these forces. Green Lake and Round Lake in Green Lake State Park, New York, are two such examples, identified among approximately 36 globally. These lakes, with their permanently layered waters, showcase how the fundamental physics of water density and chemical composition act as the primary sculptors of lake ecosystems. They dictate not only their layered structures and unique biodiversity, but also their vulnerability to catastrophic natural events and human-induced changes. The invisible architects are constantly at work, building, shaping, and sometimes trapping. Understanding their designs is crucial for managing these vital aquatic environments. These unseen forces are constantly reshaping our world, demanding our understanding and respect. The stratification of lakes, driven by the deceptively simple properties of water, forms the foundation of their ecological health, dictating their very breadth.